Hello everyone, and welcome back to another video of Stat385. In this video, I'm going to go over the 5th lab assignment. Okay, right here. And then both of these questions are going to be fairly time consuming to make videos for. So I'm going to split it up. So in this video, I'll go over the first one, comparing speed of loops and vectorization. Okay, so let me minimize. I have my RStudio window all up, so I have environment here. Wait, what? Where's my console? What happened? Minimize. Aha, there we go. There's my, sorry, not my console. My console's over here, my script, my place where I can write scripts. Okay, so I'm in my Stat385 R project. I'm gonna create, first of all, a new folder for lab 5. Okay. And I'm gonna just go here. Okay, nothing in it. Okay, so let's go to the lab assignment. So first of all, we're gonna save this script in lab 5 as vectorization speeds in here. Okay, great. So now we can see something. Okay, great, but there's nothing in it. Okay, so what we're gonna do is we're gonna consider this function as a function of x. Of course, we're going to consider vectors of a length greater than 1. And then we're going to compare implementations to evaluate this function on that vector using loops and apply functions in vectorization through different means. Okay, so simply put, this is our function. Pretty simple. Okay, so first, what we want to do, okay, so let's read the directions. With write 5 functions that take as input a single argument x, which is a numeric vector of any length greater than 0 that stores positive numbers. Okay, right, so this is actually defined quantity. Each function should return a numeric vector that is the same length as the input vector x. The elements of the return vector should be the log root reciprocal. Okay, so let's get to work on this. LRR, log root reciprocal, equals, okay, function, this is just the standard one. Normally I don't advise writing within the body of the environment, but this literally just wants log square root 1 over x. Okay, let's get a test case too. 1, 2, 4, 6, okay. So now we can just try it, and let's specify here. Okay, so LRR x. Okay, so we get some numbers. Sure, it's right. Okay, that's 1. Bad loop. Okay, so we're going to make a function that uses a bad loop that grows the results vector. All right, so let's just copy the name just so we don't get into trouble when we submit. Equals function x. Okay, so what we need to do is, actually, you know what? I'm gonna just y equals c. I'm just gonna initialize a vector. That's null. And then for I in seek along, this won't be terrible. I'm still gonna use seek along to specify the indices. And then I'm going to do y equals c y. I'm going to take this, just write it out explicitly. Okay. So now let's see here. What is y? Okay, so that seems to work. So let's put that in our function and test it out. Okay, so now we have our test case, LRR bad loop. Didn't declare it. Okay, there we go, works. Okay, so right now it looks like it works relatively fast, but we'll come back to that. Okay, so now let's do a good for loop in which we don't grow the vector. So this is the process of growing the vector, right? I have something that I've initialized to have length 0, and then as I iterate, I take what I have and I add on I combine it with a new vector, and then on the next iteration, I take what I have, add on a new vector, and assign it to y. That's called growing the vector. Okay, so a good for loop would instead not grow the vector. It would declare the vector up front. So let's call it double length equals length x. Okay, so now what is y? So y is just 4 zeros. Okay, and I'm still gonna take this. Okay, sequence along x, but now I'm gonna do yi equals just this. Is that throw an error? No, okay, good. Now what is y? Okay, it's what we had before. So let's do return y and take all of this, initialize for loop, and return, put it in our good loop function, declare it, take the name, and test it. Okay, looks good. Okay, now we will write a version of the function that uses an apply function. So again, I would normally not advise writing within the function body, but this is something that is relatively simple. Apply x, and then function name is just LRR. Right? Or you could, if you want, you could do function x and then just type it out. Maybe we should do that. Log sqrt 1 over x. Okay, just to be more transparent, I guess. Okay, let's see how it works. And we get something. Good. Okay. Great. So let me get rid of that just to demonstrate how simple this is, since LRR is already declared. Actually, no, I'm going to keep it like this. Okay, just to do an apples to apples comparison, because I could use this LRR here as well. So I just want to do an apples to apples comparison. Okay. All right. So, and now a bad vectorization. Okay. Equals a version of the function that is created by using the vectorize function on the LRR function. Okay, I need to know what this is. Vectorize. Oh, help, vectorize, okay. So I just vectorize, I just give it the function name. It's the first argument. So equals vectorize function x, and then I can just copy this. Okay. Maybe do this just to, okay. All right. I don't know, what is the standard? Maybe we do this. Okay. All right. So now I have, does this work though? Okay, looks good. Okay, so now I have 5 different implementations. I have this test case that has 4 elements. And so we can see that as I built these functions, each one of these cases performed nearly for our purposes instantaneously. However, let's continue on. Your functions will be evaluated both based on their correctness, but also their computational speed. In particular, the LR version should be the fastest. Okay, so let's test this using micro benchmark. So first of all, you need to install micro benchmark. So if you haven't, if you don't have it installed, you need to go to Install Packages, Micro Benchmark, and then you should do it. So I've already installed it. Okay, so I don't want to do this again. Okay, so now what I can do is I can take, you know what I'm going to do? I'm going to take my test case, because I'm going to change it around a little bit just to do some demonstrations. And then what I'm going to do is compare the calls. I'm going to actually do this one last. I'll take bad loop. Oh, x equals x. Good loop, x equals x. LRR apply, x equals x, and LRR bad vect x equals x. Okay, and then last but not least is our pure straight on vectorized version. Okay, so I have my, so I'm separate. So what I'm doing is micro benchmark. What it's going to do is it's going to take each one of these calls, function evaluated at x, where this is x, and it's going to call each one of these functions 5 times, or sorry, no, 100 times as the default, and compare the speeds from each one of those 100 calls, providing some distributional information about the speed, the distribution of computational speed. Okay, so it's just, what happened? Did I do something wrong? No, I didn't. Okay, let me just, at this point, we're at the end. So let me run this again. Oops, what did I do? I switched to terminal somehow. Okay, good. Now I have all my information. So now we can look at the median column, and we can see that the pure vectorized version that you would do, basically the simplest thing that you can write that has built-in vectorization does the best. The bad loop is slightly worse than the good loop, and the apply function is a little bit worse than the loops, but then the bad vectorization is not good. This bad vectorization, I guess it's just a demonstration of this point here, but it's not something we've covered in class. It just doesn't seem to be working very well. It's extra steps, so maybe that's not something that we want to do, and then maybe there's possibly rare cases where it does work pretty well. Okay, so here, let's try some more interesting cases. This is only 4 data points. R unif 100. Let's try 100. See what happens. So still in incremental, instantaneous. We can see that's it's still in nano. So first of all, this output is in speed in nanoseconds. So now what happened? Okay, so if we look at, for instance, the good loop compared to the bad loop, they were pretty close when you had only 4 values. Now it's blowing up. The good loop is way better than the bad loop. Vectorization still the best, and apply is gaining on the bad loop. Let's ramp it up a little bit more. Do something a little bit more interesting. Let's do 10,000. Okay, so now it's no longer instantaneous. And what is going to happen? Okay, we're back. So notice the unit switch from nanoseconds to microseconds. Now, the bad loop is just really bad. This idea of growing a vector, it's creating a vector inside the function environment, right? It's initializing it, and then it's calling it full out every single time you grow it. Whereas in the good loop, you're just declaring a big vector up front. Oops, sorry, I should be looking at median. You're declaring a big vector up front, and you're just then assigning specific elements, specific values. You're not referencing the entire thing from memory. So it's this explodes in computation time as you increase the number of elements inside the vector. Here, The lapply function, or sorry, the good apply function is technically there's some overhead in converting it into what is ultimately going to be a for loop under the hood written in C code. So there is some overhead happening. And so the comparisons between good loop and the apply functions involve sort of the complexity of the task that you're using. Here it's relatively simple. But also when you're doing this, there needs to be some understanding of the scope of the task that you're working on. So for instance, on these one-off coding assignments, then what should factor into your computation is what is easier to write. Is it easier to write this code, or is it easier to write this code? And if you have LRR specified, you don't really need to even go through this, because you could just write and then done. Let's see what happens when we do that. Okay, so it's gonna take a little bit of time yet again. You know what, actually, I'm gonna kill it because I don't really wanna look at this bad loop anymore. That's just bad. We don't wanna do bad things. Okay. A little bit of savings, I guess, but that could be within error bars. Another thing that's going on with sapply, and we didn't cover this too closely when we originally covered apply functions, but here when you're looking at incrementally improving things computationally, sapply sort of has to guess at what the type is. We can consider another function called vapply. And you know what? That's probably good. Function value here, this argument, if you declare it up front, it doesn't have to go through the process of guessing what it should be. So let's try that. Okay. Vapply LRR double one. Yeah, that really brought it down. Still, the good loop is pretty good. So then it just becomes a trade-off, which is sometimes a bit of an art for understanding what is the overall cost what is the overall cost in time of actually writing the code plus the time savings that you would get from optimizing it in terms of this sort of like benchmarking way and factoring in computational speed. And that can be a bit of an art too, but keep in mind that this good loop function requires that you actually write a good loop. And if you have the tendency to write code this way when you want to write it this way for computational reasons, then this is going to eat into your development time for the functions that you're trying to create if you have to constantly switch because you realize that one is going slow. So apply functions are very concise, easy to understand, and easy to write and communicate. But the main message here is that R works with the principle of vectorization, and that's kind of its default way of operating, and all of these functions, square, root, and log, both operationally are these sort of embraces vectorization concepts so that they can work on all of the elements of the vector of the input vector, and you don't really need to build an apply function on top of it. So if you can understand vectorization, then this is where the conversation starts and stops, and that there's no real reason to go through the game of for loop and versus apply. So keep that in, that's the main message here. So I guess let's just run through it. So if you can do this is absolutely what you're going to want to do, embrace vectorization. If you cannot, you need to avoid growing the vector with for loops. I think a common criticism of R from outsiders or beginners, especially if they're coming from other programming languages, is that R is slow. And that's not a fair criticism always, because R may be slow because people aren't actually writing R in the way it should be written to make the code actually fast. And if you're doing this, then yes, R is slow. That is correct. But that was a lot slower than than writing something that embraced vectorization. Let's go back to the benchmark again, and let's add, I don't want to blow up the computational time. This is still going to take a little bit. Let's just cut it in half. Let's do 5,000. Okay. Bring our bad for loop back into the mix. So let's take our median time for the bad loop and our vectorized function, and see here that when we had 5,000 elements, vectorization is 700 times faster than the bad for loop. It's also 8 times faster than a good for loop. .8, that's close enough. Okay, so here, and this goes back to the point again, not only is this easier to write than either of these, it's also just much faster. So do this when you can, and then if you can't, then either of these is going to depend on kind of the overall scope of whatever it is that you're working on. But if you are trying to productionize code in a way that for tasks that are going to be used repeatedly by you or other people or many other people, then I would recommend a careful study between this and this, and you can use this micro benchmark function inside of the micro benchmark package to make the determination similar to what we've done here. Okay, so let's wrap this up. And I don't think I need all of this for this submission. I just need these functions. Okay, so let me see here, drop. I don't know how much, I forget how much time this is actually going to take to do my submission. Why is that? Okay. I want, wait, I'm in stat 430. Did I do something wrong? Oh, did I? Oh, wrong, wrong class. Okay, save and grade. Okay, that might take a while, so I think I'm gonna end here. Okay, so I will see you next time doing S3 methods. All right, thank you for your attention and take care. I'll see you next time. All right, bye.